Hi everybody, welcome back. One of our previous videos we looked at the time displacement between voltage and current and how the voltage across the capacitor takes a period of time for the capacitor to charge and what happens with the light bulb. So what I'm going to do here is just kind of break it down and look at what current is doing inside of that circuit, because capacitors are fascinating things. Capacitors, we have two metal plates separated by a dielectric. And it's really important to remember there's no current flow through that dielectric. If there is, it's a problem. Our capacitor needs to be replaced. But the intent is that this is an insulative material. So when we look at this circuit, we kind of think, well, if that's an insulator and there's no current flow through past it, current flowing through it, how do I ever get current flow? I basically have an open circuit. So what we have to look at is the property of the electrostatic charge on the plates that's actually allowing current to take place. And one of the things that we remember is that that capacitor, it has electrons already sitting there, okay? That capacitor, when it's sitting de-energized or discharged, it just means that there's no potential difference. The electrons, they're balanced. So let's just say there's 3 and 3. So at our source, we have a negative plate, meaning there's a collection of electrons at that point with respect to that positive terminal. So as soon as I close this push button, we really have no opposition from that negative terminal to this point right there on that plate. But the capacitor is sitting charged. So because I have no opposition, let's imagine that there's one electron that travels through that circuit and reaches that plate. Well, as soon as that one electron, because that capacitor is trying to stay de-energized, that's its purpose, is to stay at an equilibrium, no voltage. But when I have an electron enter that plate, it's going to force one of these electrons off of that other side. So the electron never passes through the insulator, but there's a force that repels it off of that other plate. So we see we have current flowing through our circuit. And at that point in time, I'm going to start to have a voltage appear across that capacitor. It's going to start to charge. Why? Because now I have an imbalance of electrons, a potential difference. That light bulb came on bright instantaneously. If we think of Kirchhoff's voltage law, this was a 32 volt source. So that voltage has to exist at some point. It was 32 volts across that light. That's why it was bright instantaneously. After a period of time, we're going to have that capacitor reach a maximum value. You've seen the needle move up and the current needle going back down to 0, because when I have 32 volts and that capacitor is fully charged, now I have two forces that are opposing each other, no current flow. Now, when we reach that point and I had that capacitor fully charged and I have all of those electrons built up, I let go of that push button, that capacitor stayed fully charged. Then when I went to discharge that capacitor, I de-energized the other push button, depressed the other push button, closing that discharge path. So all of these electrons collected on that one plate, and now they have a path to leave that plate. That's why we see current moving in the opposite direction. The needle of that ammeter moved the opposite direction. So all of those electrons are flowing through that light. The light went bright immediately because initially I'm going to have 32 volts across that light bulb. Eventually, after all of those electrons travel back to the other side and we have that equilibrium where there's no potential difference, there's 0 volts across that capacitor, Kirchhoff's voltage law says there better be 0 volts across that light. That's when the light was out. Now I have no current flowing on that circuit. Hope this has helped to see what's happening with the capacitor. See you next time.